what we're doing now is a pitch-off, which is kind of a slimmed-down version of that. But we're slimming it down again because this time we're focusing strictly on the technology. We've got 3 companies/projects that are going to present and 4 judges that are going to assess those projects. So with that, I'm going to introduce our very esteemed judges. Please welcome Jeremy Conrad, who is a partner at Lemnos. It's a seed stage investment firm based out of San Francisco. He's also in the Air Force, which is badass. Then we have Helen Grenier, who's the CEO of Sci-Fi Works. You guys remember her from earlier today. She was a co-founder of iRobot and served as president until 2004. We have Daniel Theobald, who is the co-founder and chief innovation officer at Vecna. Did I say that right? Damn. Okay, cool. Also a big robotics company. And then Melanie Wise, who is the CEO of Fetch Robotics. Advanced robotics for the logistics industry. And this is not her first robotics company, so bravo to you. Brava. Okay, our first company is Tangible Media Group. Daniel Fitzgerald is presenting. Come on up here, Daniel. It's like the most Boston name I've ever heard. You ready to go? Okay. Take it away.
Hi, everyone. My name is Dan Fitzgerald. I'm not from a company, but I am from a lab down the street at MIT. And I'm going to talk about robots, but before I do, I'm going to talk about virtual reality. So today we're witnessing the convergence of 2 worlds. First, there's the physical world, which we can see and touch, and we can manipulate directly with our hands. And then there's the digital world, where we have incredible power over information, but today, information lives behind a screen, and it's kind of ethereal in cyberspace. But with the advent of consumer-level virtual reality, augmented reality, these worlds are coming together. These dimensions are bleeding into each other. So if I put on this headset, I can see a complete virtual world, which you can't see. But trust me, it's really cool. And I look ridiculous. But the problem with VR today is that if I try to reach out and touch something, my hand goes right through. So there's no sense of touch. And touch is the most important sense for interacting with something physically. My research group at the MIT Media Lab is on a mission to bring physical form to computation, to make information tangible. Next slide. And so other people tried to do this before with VR gloves and with in-air haptics, but again, the problem is that none of these technologies really feel solid because, again, there's nothing physically there. And my research group is pioneering a technology that we call shape displays. So if you think of a screen that can display information, visuals, images, we are making technologies that can display shapes. They consist of an array of pins, and every pin can move up and down. But when they move in coordination, they can recreate the rough shape of 3D computer models. And we've used this for a variety of applications, from physical telepresence and collaboration to computer-aided design, which you can see here, to interacting with medical imagery, having hands-on learning for mathematical functions, interacting with dynamic topological maps and urban planning, and all these different applications and many more. The problem with this technology is that it's incredibly difficult to scale. These devices are big, they're bulky, they're expensive. And if you wanted to have an entire room-scale experience with virtual reality and add a tangible component to that, you would need a shape display as large as that room. And it would be completely impractical to fill a room with pins. So we thought, instead of making a larger display, what if we make a smaller display, just the size of a hand, but make it move around the room intelligently so it can anticipate where interaction is needed. So that's the goal of the project I'm here to present today. The system consists of a small shape display, 50 pins, but it's mounted on an omnidirectional robotic base. This entire device is tracked in 3D using the same system that the virtual reality uses, but it's also aware of the user and where their hand is. The idea is that as long as the display knows where I'm about to reach, and it can position itself there in time, and if it knows the virtual geometry that I'm supposed to be touching in that place, and it can render that geometry before I'm touching it, then from my perspective, with my headset on, the entire virtual world becomes tangible. Let me show you what I mean.
Quickly. I'm concerned you're running short on time.
I have one real ball, which is right here. And now I can use my robot to track my hand. Oop, if I don't get caught up in wires. And this is just following my hand, so I can guide it around a virtual room. And it knows exactly where it is. And then somewhere in here, I have a virtual ball. Let me see if I can find it. I have to play hide and seek. Oop. There's a spot on the floor somewhere. Here it is. I don't know if you can see this, but the idea is that the geometry of the ball stays in place even as the robot moves over the ball. I can tilt this to give you a better idea of what I mean. Oh. There it is. So the geometry is now rendered from the physical world, from the virtual world to the physical world, and now I can actually touch and not look quite as ridiculous. So my hope for this technology is that robots in the future will be an arbiter between the physical and the digital worlds, and that they can act as our shepherds into cyberspace.
Okay, great job, Daniel. Judges, to you, thoughts, questions, concerns?
Yeah, how close to kind of scalability is it? I mean, I see you've got the big tether. Is it mostly hydraulic? If, Disney came in and said, we want 100 of these, could you actually go and then build that number of them, or is it still pretty,
So the great thing about this is that you only need one robot for each hand. So if you have one user, 2 hands, you need 2 robots, 50 pins. It's not great, but it's much better than an entire display of thousands of pins.
What resolution are you thinking about on the tangible display?
So of course, we're always trying to get better resolution. One of the things you run into is if you make the pins too small, they become sharp. So that is actually a limitation from a user perspective. So we found that this size of around 20 millimeters is a good size to go with for rough shapes.
And have you thought about any membranes over the surface to provide that smoothing?
Yeah, there's various ways of kind of smoothing out that surface and interpolating between it. We find that this is analogous to voxels and has a good compromise between resolution and smoothness.
So this is great for static scenes, but what happens when you want to pick up the ball and throw it?
So the idea is that we have 2D or bidirectional interaction. So I can feel the ball, but I can also push on the ball. And of course, this is limited in the directions I can push it and so on and so forth. The idea is that if you add more degrees of freedom to a system like this, then it becomes a way of tangibly interacting with those virtual objects. And also, the objects can be moving. This ball could be moving in the room. The display just renders whatever is there, whenever it's there.
And then how do you do the synchronization? Who is the lead? Is it that device or is it the VR? And how do you keep people from throwing up?
So the VR is this device is just an interface, the same way that a screen would be rendering the virtual world. Whatever is happening in the virtual world is happening, and then this is just an interface to that.
And the throwing up question?
Oh, well, so for example, I can interact with this sphere without putting on a head display. So this kind of eliminates motion sickness if I can now interact
Yeah,
with
but
that.
it's less fun. Nobody wants to play with that without a headset. I mean, no offense or anything. But.
I have interacted with the headset. My goal for this is that eventually you won't need a headset because you'll have an interface that can have both color and light and visuals and tangibility all in one device.
So right now, if in your VR world you pressed on that ball and made that go down, would it actually bounce? Or
In this
something?
version, no, because I've disabled interactivity, but I can push on it. It's actually quite strong.
What would you say the pros and cons are of this approach over like a Phantom, that was designed here at MIT years ago? Basically a robot pushing back on your fingers.
So I think the advantage of this system is that it's very adaptable and general. So this can render any geometry. I could have a virtual car here and feel the contours of the surface of the car, for example. And basically any topography I can render with this general system. If you have other specific haptic systems, you're usually having a wand or a pen or something, and that has force feedback, but it has its own form factor.
Really? No more questions? How far are we from this being commercialized? I know you work at a lab and not at a company.
This is a research project, so I can't say anything about that.
Okay, fair enough. Nothing else, folks?
But what do you see as the killer app for this? I mean, where
So
is
for
it
me,
going
video
to make a
games?
difference? Where is it going to disrupt a market?
So I'm imagining if you're playing in VR video games, then you can now have actual physical cover or physical interaction with the objects in the game. But I think there's even bigger applications for computer-aided design. If I'm a designer and I want to have fine physical control over my design instead of interacting with the computer, now I can just use this as kind of a digital clay and sculpt in physical world.
And do you see it being something where, as other speakers earlier today mentioned the importance of the cost versus the value it provides? I mean, this is obviously a pretty complicated device. Do you see the price coming down significantly once it leaves the lab? Or
so hardware is obviously harder than software. Pixels on a screen, we can double their resolution every few years, and that's no big deal. Doubling the resolution of a thing that has many, many motors is much harder. But I think that this is kind of a compromise between if you're a high-end designer and you have some budget to spend, maybe not for a consumer level, but for a company level, where they already are investing in these types of devices that lets them have finer control over their design space.
So you don't see one of these in everybody's home?
Not for a couple of years.
Fair enough.
Awesome. Thank you so much, Daniel. Awesome. As he wiggles that thing off, we're going to bring on our next guest. It's Rory McKean from Franklin Robotics. Come on out, Rory.
The information is all changeable, right? It's the it's a theory. It's the concept.
Do you have the...
We were like, let's throw a robotics show, and then we realized that there are a bunch of big robots around, so it takes a little time to... Rory, can you hear me? There you are. Okay, cool. 4 minutes whenever you're ready.
All right. My name is Rory McKean. I'm the CEO of Franklin Robotics. We're a startup outside Boston, and we're developing outdoor robots. We've heard today that building hardware is hard, and building an outdoor robot which is mobile and intelligent is even harder. Our unique advantage is that we've done this before. Our team has designed, built, and shipped robots at scale and around the world. I met my co-founder, Joe Jones, at a company called Harvest Automation, where we worked together on an outdoor robot for agriculture. Prior to co-founding Harvest, Joe was an early and long-time employee at iRobot, where he is one of the inventors of the Roomba. Joe and I share a passion for simple, practical robots, and we got really excited about the idea of making a robot for outside the home. And when you talk to people about what they do outside the home, you find out that people really enjoy gardening. It's a hobby that they're really passionate about, and they want a healthy, relaxing, safe place for their family, for their pets, and for the environment. But the weeding part sucks. As we get older, it gets harder to bend over and pull the weeds out by hand. Even when we're young and healthy, it's time-consuming, it's frustrating, and it's no fun. But if you want a healthy and productive garden, the weeding needs to get done. So what can you do? You can put down Roundup or some other chemical. If you care about the health of the environment or your family, or you're growing food for your family, that's not something you want to do. You can pull the weeds out by hand, but that's no fun. Or you can let a robot take care of it. And so we came up with a better idea, and we call it Turtle. So Turtle is a solar-powered robot that lives in a vegetable garden or flower garden. And every day, it'll charge itself up in the sunlight. When the battery gets full, it'll wander around the garden. It avoids any plants or obstacles or anything that's taller than an inch. And as it's doing this, it's always looking for any weeds which are growing up from the ground. And if it finds them, it'll cut them with a little weed whacker that's on the bottom of the robot. So Turtle is sized to be big enough to climb over the obstacles that you see in a typical household garden, but small enough to fit between the plants and have some room to move around. It's waterproof and solar-powered so that you can leave Turtle outside in the garden. And that is what lets us get away with the chemical-free approach of putting a weed whacker on the bottom of the robot. So every day, Turtle is out there continuing to cut the tops off of the weeds, which eventually starve and die. It's simple to set up and use. There's no mapping or programming required for the user. And it has a robust sensing approach that isn't prone to getting dirty and occluded like a typical vision system would be. And it has a Bluetooth connection if you want to check up on the robot and see what it's up to. So we just closed our Kickstarter campaign last Tuesday, and we're super excited. We got over 2.5 times what we were looking to raise, and we have 1,200 backers that are really excited about getting Turtle into their garden. And so Turtle is a really simple, novel approach to getting rid of the weeds. And when you think about the applications beyond the home garden, getting rid of weeds in a non-chemical approach is something that is quickly becoming a necessity. The promise of herbicide-resistant crops has given way to the reality of weeds that grow even faster and are tolerant of glyphosate. So we need a better approach, and this is what we're working on. So if you want to learn more about what we're up to, you can visit us at franklinrobotics.com. And if you're interested in getting a turtle for your garden, or even though our Kickstarter is closed, we're still accepting pre-orders, and you should get a weeding robot for your garden, because weeding sucks. You should make a robot do it. Thanks.
Awesome. Franklin Robotics. Judges, to you.
You know, I was just doing a whole bunch of weeding just a few days ago, so this is near and dear to my heart. But the ground that I was weeding on was much rougher than I'm seeing in that demo. Can you address that?
I can. It is hard to transport a garden for demos, which is part of it. So we test on soil, we test on mulch in a variety of different conditions. We set up a garden outside of our office just for this. So we made sure that mobility was one of the most important things that we spent a lot of time testing. So mobility and sensing were the two things that we focused a lot on. And that's how we ended up with this sort of unique drive geometry, which turns out, though it was unintuitive and took us a while to get there, to be really capable at climbing over obstacles and not getting high-centered and stuck on various things. So we software limit the slope to 40%, which is about 22 degrees. And what we found is a lot of gardeners will sort of mound their vegetables. And so that's something we definitely wanted to address.
And just a quick follow-on question, sorry. How does it deal with the rock? I mean, does it weed whack the rocks too?
So if the rock is tall enough that it's an obstacle, the robot will sort of bump into it and drive off. If it's small enough that the robot drives over it, it may or may not try to weed whack it.
Yeah.
So a follow-on question to that, you have to put more thread out in a weed whacker once in a while. Does the robot do that?
Yeah, so the robot doesn't, we don't have an automatic string mechanism. So part of that is simplicity. But we have a couple advantages over traditional weed whacker.
Do you change it once in a while?
Sorry?
Do you change it once in a while?
You do need to change it once in a while.
Okay.
One is that we don't run the whacker as fast as your typical weed whacker. The other is that we don't run it nearly as often. So the weed whacker runs maybe 5 or 10 minutes a
Unless
day.
you hit a rock.
And we're not cutting grass on a regular basis, and we don't need to deal with stumps and tree roots and things like that.
Now
So
you mentioned
it's a much
chemicals
gentler
as
environment.
a competitor. What about mulch or putting down a plastic bag?
Yeah, so people have been dealing with weeds for a long time, and there are a million different approaches to getting rid of weeds. Mulch is something that people do. It typically requires that you put down more mulch every year. So it's an alternative. It's also labor intensive at the beginning of the season. Plastic mulch is something that people put down, ground cloth, people call it mulch. And that's one approach. It's not nearly as nice looking or pretty, and also requires that you put it down and do maintenance on a regular basis.
From a computer vision perspective, can you talk a little bit more? I mean, you've got kind of an idealized garden right there. It's like, to the kind of point about like rocks earlier, is it possible for it to kind of get stuck in loops and just like try to repeatedly kill this rock that's right here and like not make it to the rest of the garden?
Yeah, so a couple things. So we're not using computer vision, as I mentioned. So we have sort of a capacitive sensing approach on the front.
Okay,
so it's not vision-based.
Okay.
Outdoor robots frequently get dirty, and it's really hard to keep vision sensors clean. We think about the robot not getting stuck quite a bit. And so Joe's expertise in developing the Roomba comes up all the time in dealing with situations like this, where at a naive level, it's simple to make it sort of turn and bounce when it gets things. But you need to get a bit more clever to think about how do you extricate yourself from these situations and how do you not get into them in the first place. So we spend a lot of time on that as well.
Like people are inherently lazy. And so like if someone screws up and they wait a couple weeks and suddenly they're over an inch, is it capable of actually taking care of weeds once they're there? Or is it, okay, you waited like 3 weeks, you're screwed, now you got to get out there and do it by hand?
If the weeds get tall enough that the robot can't tell the difference between plants and weeds at that point, so you would need to run around and pull the weeds out. You do have the benefit where you can just kind of run through and do it quickly. You don't need to get the root structure out like you would if you were weeding by hand. But you will need to run through that because it is height-based.
Got it.
Melanie?
Yeah, I was wondering as a user, how do I know when I'm supposed to maintain this robot?
So the idea is that it lives out in the garden, and there's not much maintenance you need to do. Inevitably, the world will intervene, and there'll be something that goes wrong, and it'll need help. And so that's why we made it Bluetooth connected, so it can tell your phone that it needs help. And so that's sort of our primary mechanism is, letting you know via audio cues.
Bluetooth
Has a
from a
Bluetooth
garden,
connection.
from the garden in your back of your house, through your house, into your house, and connected
So
to
the
your
idea
phone?
is we are not replacing gardening. We don't want to have an all-in-one gardening solution. And this is sort of one of the important things that we thought about when we got into this area, is we don't want to replicate the fun parts of gardening, but the really crappy parts. So the idea is people will be out in the garden anyways, on a regular basis. It might not be every day, but once a week or so.
But if my robot gets high and dry or something's wrong with it, and you just told me that I have to go weed the garden if it grows more than an inch, like, could that happen in like a 1.5 week period? I mean, then you're basically not doing what the robot wants. You're doing what the robot's doing it, right? Because you aren't getting notification instantly.
Yeah, so it's possible that if you go away for 2 weeks and the robot gets stuck on day 1, that when you come back, there's that there may be weeds, and that's something you'll need to do. It's tough to get perfection at a consumer price point. So
Which is what,
Would
by
have
the
never
way?
guessed.
so our pre-sale price is $249. We expect our retail
MSRP?
price to be $300.
300. Cool. Great job.
Thanks.
Thank you very much. Franklin Robotics with the turtle. And then we have one last presentation. It's coming from Claudia Perez Darpino. And she is an MIT PhD candidate. Claudia. Claudia.
Price.
There she is. Okay. Make an entrance. Okay, you have 4 minutes to present your project.
So humans spend 30% of their time doing not value-added work on the factory floor. Today, the tasks are either 100% automated, such as welding here on the left, or 100% manual work here on the right. On a rapid transition to automation, the best way that we have to add value to this process is to put humans and robots working together on the factory floor. But that poses some challenges that we haven't thought about before in robotics. So today, I'm here to present technical contributions that I've been working on in enabling robots to make predictions of the human motion so that the robot can better predict what the human is going to do next so that it can be a better and fluent collaborator. And if we really want to go further with automation in collaboration with humans, we need these robots to be able to learn how to execute manipulation tasks directly from humans from demonstrations, as opposed to having an expert programmer teaching the robot how to do it just by coding everything all the time. So we have developed an algorithm for real-time motion prediction in which the robot observes the human executing different manipulation tasks, and it collects this data. And then the algorithm will produce a statistical model of how the human is moving for all these different possible tasks, and then keeping that in memory so that later we can execute real-time motion prediction. In the blink of an eye, about 400 milliseconds, we can predict for at least 70% of accuracy what is the target of the reaching motion. Can you predict what the person is next to you is about to do just in the blink of an eye? Can we go back, please? OK, so now I'm going to show you about how we can teach robots how to execute manipulation tasks by only providing demonstrations. We have developed C-Learn, an algorithm called constraints learning, where you can teach robots how to execute multi-step manipulation tasks by using this video-like user interface, where the user is dragging around the hand of the robot, and the robot can infer these constraints. So more technically, we are taking data from human demonstrations, clustering that data to recognize keyframes, or very important moments in the manipulation, and then infer geometric constraints that are then later used to invoke an optimization-based motion planner to produce these motions, for example, for assembly. So here, for example, you can see a robot Optimus, a 16-DOF mobile manipulator, executing one of these manipulation tasks that I showed before. And here you can see really how the robot is going to grasp the handle of the box to secure the box and then extract the cylinder. You really need to move in a line to extract this cylinder from the concentric one. And these are constraints that we were really not able to learn previously with previous learning from demonstrations methods. So in the next video, you will see how we have a side effect of learning constraints, which is that now you can transfer this knowledge into a robot with a completely different body, a completely different kinematics. More technically, what we are doing is taking these geometric constraints that you can write explicitly and changing that into a new robot with different kinematics. And you might know that this one now has to balance. So it's different requirements. So imagine that now you can upload the brain from the person next to you, and you can learn to, I don't know, dance salsa, speak Spanish just immediately. That's what we're trying to do with robots, so that we can transfer these tasks to a different factory, probably even in a different country. So I truly believe robots will empower us to maximize our brain power. So what are you going to teach your robot?
Very good job. Thank you, Claudia.
So you said that it's accurately predicting about 70% of the time. How good do you think you have to get it before you could really deploy it out in a factory?
Say that again?
You said that about 70% of the time it can predict where the human's going to go.
That's right.
So
Yeah.
how good do you need to get that before you can deploy it?
Yeah, it will really depend on the specific tasks that we're talking about. For the ones that we have studied, 70% is certainly not enough. But when we analyze further the result of the algorithms, we have discovered that if you are willing to give up a little bit the accuracy of the specific target and consider that the neighbor target is good enough classification, then we get to 100% basically. So if you're willing to classify for a larger area, basically are you going left or right, that would be 100%. And depending on the size of the table, that would be really enough for the robot to plan to go to another side of the table so that it can move around you.
So manufacturing, in what industry do you think is the best initial target for this technology?
The application I've been considering so far is car manufacturing plants. So for example, let's say when you have to install parts on the dashboard of the car. So right now, this is done just purely manually, because we don't really have robots, at least yet, that have the dexterity to install this inside the dashboard. But then workers are walking around to get the dashboard, to get the meter, to get the tools. So what if a robot could predict at both the motion and task level what is the next step, so that now a robot can go ahead, retrieve the parts, and offer them to the human?
And does this C-learning and these type of interactions, are they model-based approaches? They require us to have 3D models of the objects that we're manipulating ahead of time?
That's right. The way we have worked yet with it is model-based. So we have the geometric concept of a cylinder, of a box, and other simple shapes. If you think about it, it will still work for different parameters, so different radius, different length, but you still need to be able to classify that these objects are specific shapes that you have in the knowledge base. Of course, with more advanced perception, you might be able to generalize that, but then we're getting into perception.
So it sounds like in order to solve this problem for the constraint-based planning, you need a fully analytical solution for the robot kinematics. And how does that work with robots with continuous joints? How does that work with robots with nonlinear joints? The types of robots that you might need to do these tasks.
So with the learning we are doing is really on the n-effector space. So we are thinking about how you need to move your hands, basically, with respect to these objects. And the specific kinematics and specific actuation and nonlinearities there, we're making an abstraction. So we are thinking this is obviously for quasi-static settings, where you can assume, and rigid objects, where you can assume that they're not jumping around. And then with that, you can do a plan in advance. This is the object, I'll plan to reach there. I can even show it to the user to see if the user agrees or if it is incorrect.
Yeah, so just to be clear, this is constraint-based grasp planning.
That's correct.
Okay,
yes.
I just wanted to...
And once you have grasped, it will also do transportation and locate the object in a different position, but also quasi-statically.
Okay.
Yeah.
How might this integrate with other approaches to determine the human's intent? I mean, obviously, if I'm reaching for something, maybe you can infer intent, maybe you can't. Is this a standalone thing, or might it be part of a bigger
Like you're scratching your head, and it's like the robot starts.
It is definitely part of a bigger system. So I envision this system, if really implemented on the factory floor, being a hierarchical system where you have even not only one predictor, but multiple predictors, because they might be better for different regimes and different dynamics of the tasks. And also, we have to have a last layer of safety. So what if the predictor makes a mistake? That is not really acceptable.
Right.
So we have safety by actuation, so maybe the robot can stop, or safety by perception, where you recognize you have done a mistake and then you stop. But we also need safety at the auto level of we need to be reactive. Like we make a mistake, let's stop.
Right, right. In the real world, that's going to happen a lot. So is there a sense for how the human operator communicates to the robot that they've made a mistake, or is that future work?
So in the framework that we have so far, you would need to discover that in the moment that the robot shows a visualization of what has been learned. So through this like video-like user interface, or 3D user interface, RBs kind, the robot can show to you an animation. So this is the object, and this is what I will do when I see this object. Do you agree? You don't. So it will need to be at that phase that you discover the mistake.
Thank you.
Awesome job. Thank you so much, Claudia.